Here we'll have a quick look at energy budgets again before we can start to understand regional climates a little bit better. Why do we care about energy budgets? They determine the overall climate. They determine local variations in climate. They determine the response of climate to human-forced changes and to natural changes as well. And changes in the local energy budgets can actually induce circulations, for example, sea breezes, mountain valley circulations, and more. As a reminder of what net radiation is, net radiation R equals downwelling solar radiation, shortwave radiation in, minus short radiation up, plus longwave radiation in, minus longwave radiation up. Another way to write the shortwave radiation is the direct radiation, large Q, plus the scattered radiation. Anything scattered from gases or clouds is considered scattered and not direct sunlight. So the combination of those is the total direct beam coming down. Multiplying times 1 minus albedo gives you the proportion that's actually absorbed at the surface. When we're talking about the albedo with a surface radiation budget, we're really talking about the albedo of the land surface, not considering clouds. Clouds change Q plus Q. Here's looking at the components of the surface radiation budget measured at a location in the Great Basin, cloud-free in September. How do we know it's cloud-free? Well, there's no deviations in the incoming sunlight here, big Q plus little q. So it makes a nice bell curve, and that's how you can tell it's a cloud-free day. If you take away the albedo here, Q plus Q, 1 minus albedo, or the net shortwave radiation, you get a reduced amount. And you can see you have an excess of energy during the day, as you might expect, and you have no energy from solar radiation during the nighttime, as you would also expect. Outgoing long-wave radiation is up here, shown as an energy flux in watts per square meter. Almost always the outgoing long-wave radiation is higher than the downwelling long-wave radiation. And this is because the outgoing long wave is coming off the surface, which is typically more warm than the existing atmosphere and greenhouse gases. So the surface is responsible for giving you the outgoing long wave, and the gases and clouds are giving you the downwelling long wave. The combination of the net short wave, the dashed line here, plus the combination of the net long wave, which is the combination of these two, give you R, the total net radiation. And you can see, although you'd have an excess during the day, which is dominated by the impulse of solar, you do have a deficit at night because you're giving off more long wave radiation at nighttime by the hot surface than you're getting back from the greenhouse gases and clouds in the atmosphere at nighttime. Now, ATOC has instruments where we can look at a few of these things. We'll look at the pyranometer, which is an instrument that looks at that incoming shortwave radiation. It's just looking at the component that's coming in directly, but also scattered. So big Q plus little q. So the scale here in time is in UTC. UTC for daylight savings, you subtract 6 to get the local time for Colorado. So the sun came up around 6:30 a.m. As it came up, there was a small cloud event here. And then you're going up, up, up. It was pretty clear for most of the day. Then we started to get afternoon clouds, and you can see all these holes punched in this direct solar beam. The day before, you can also see clouds in the afternoon and night. The last thing you'll simply note here is that, yes, there's no solar radiation during the nighttime, as you know. The purgeometer, on the other hand, measures downwelling long-wave radiation coming from the clouds and the gases in the atmosphere. And here, it is a function of temperature. Primarily, it's a function of atmospheric temperature, especially on a clear day when those greenhouse gases get to their hottest moment. They're going to have the most downwelling long-wave radiation based on the Stefan-Boltzmann law, and you're typically going to see large amounts of long-wave radiation coming down at that time. However, clouds have a large effect on downwelling long-wave radiation. Clouds effectively trap a lot of long-wave radiation near the surface. Or another way of saying that, clouds are massive and low clouds are warm. They give off a lot of IR radiation towards the surface. Here you see this was going up slowly as we got past noon into the afternoon hours where it was probably warmest in the atmosphere, but then it jumped up all of a sudden. So why did it jump up? Well, looking at the pyranometer, you see it's in tune with the clouds. When clouds came in, the downwelling long-wave radiation jumped up. Just goes to show that clouds do trap a lot of IR radiation near the surface, or again, they emit a lot of IR radiation if they're low clouds. Here's another spike we saw the day before, and lo and behold, it does line up pretty well with a dominant cloud that blocked the solar radiation at the same time. The final instrument you can look at to confer these things is the ceilometer. This shoots a beam straight up. It hits a cloud, comes back down, and measures the time it took for that to happen. In so doing, we can figure out how far away the base of that cloud was, or if there was a cloud there in the first place. And this is showing some cloud activity here that correlates with the gouges in the solar radiation beam, and also correlates with the increase in long-wave radiation coming down. Now for the surface energy budget again, we have the net radiation equaling three components. The first component is the latent heat flux. So this is a function of how much evaporation or transpiration you have. That would be a loss of heat for the surface, or it could be condensation or deposition of frost on the ground, which would be a gain of heat for the surface. H is a heat flux to the atmosphere, the sensible heat flux. How that happens is that the warm surface conducts heat to the really thin layer of air above it, and then convection takes that air and moves it in the fluid. And so by the process of conduction and convection, you can sensibly transfer heat from the ground to the overlying atmosphere. Now it goes the opposite direction. If the temperature gradient goes from a hot atmosphere to a cold ground, the sensible heat flux goes into the surface in that case. The last thing is the heat flux into the ground, G. Now that's the conduction. If you warm the surface, it doesn't just have to heat the air or evaporate water, it could also conduct energy, conduct heat downward, and start warming or storing heat in the deeper ground. And of course, if the ground's hotter than the deeper ground, G will go away from the surface and move heat down into the ground. However, if the surface becomes colder than the deep ground, the energy goes the other direction, following the temperature gradient up from the deep ground. So looking at each term a little bit more, the latent energy flux, it depends on the moisture availability, of course, and the amount of plants. How much moisture do you have to evaporate? Or how much snow do you have to sublimate? It also depends, however, on the turbulent transfer of that water vapor. So it's not enough just to evaporate water from the surface. You must have some kind of convection or winds or turbulence to remove that water vapor away from the surface so you can evaporate more. What would happen without that turbulent transfer? You'd get some evaporation, and then the air just above the ground would become saturated quite quickly, and that would shut down evaporation. So it's a very important term to understand that turbulence will remove that moist air and replace it with drier air so you can evaporate more. And this feeds into the idea that you have fresh vapor supplied by evaporation, turbulent transfer removing it, and then you can get further evaporation and the turbulent transfer goes on and on and on. It can work the other way, however, when turbulence can mix down really humid air that then condenses to the surface during dew formation. That takes away a lot of the water vapor near the surface, so it needs to be replenished by moisture above and it gets mixed down so you can form further dew. Sensible heating, it depends on the temperature difference between the ground and the air and the efficiency with which turbulence can move that heat up and down. H is a negative term if the air is warmer than the ground. And this happens a lot during the winter. Here's just a look at your typical eddies and what we're talking about with turbulent transfer. During the nighttime, you have small eddies with frequent wind shifts. The eddies are small because they're typically driven by wind shear in the vertical. Winds typically will increase with height. That tends to drive these circular circulations called eddies, and they tend to be small. And these eddies will move around and cause frequent wind shifts as they move around. So you'll get little wind shifts happening during the nighttime. However, during the daytime, you get those small eddies driven by vertical wind shear, but you also get much larger eddies that are driven by buoyancy. In other words, warming air at the surface becomes buoyant, rises up and starts making these larger eddies as drawn in the center of this picture. So when these things start moving around along with the smaller eddies as well, you get more pronounced wind shifts happening. One can measure this with what's called a bivane, and this is a wind vane that doesn't just go in the compass directions, it also can rotate up and down. So it really gives you a measure of turbulence by seeing how much the winds fluctuate up and down. So we're looking at the wind inclination from minus 10 degrees pointing down to plus 10 degrees pointing up. And you can see during the nighttime it does shift around, going up and down quite quickly, but no large deviations here. And that's because the eddies are smaller. During the daytime, much more fluctuations, going almost to 20 degrees pointed down to 30 degrees pointed up. So you have these larger eddies forcing larger amounts of turbulence, and you can also move a lot of heat by these larger turbulent eddies. So the overarching point here is that the turbulent eddies are actually important in the energy exchange going from the surface to the atmosphere, both for latent heating, moving water vapor up vertically, and also moving heat up vertically. Now the conduction in the ground, what does it depend on? It depends on the thermal conductivity of the substrate. How conductive is the material? Is it sand? Is it rock? Is it dirt? Is it water? Thermal conductivity increases with soil wetness. So here we're showing increasing soil moisture to the right, and the conductivity is little ks here. going up on the y-axis. So you can see as you add a little bit more moisture to soil, it makes it much more conductive initially. Eventually you reach a point where the conductivity doesn't go up as much with increases in soil moisture as it gets really saturated. So how much energy does it take to raise the temperature of that soil? Heat capacity definitely increases, and it increases linearly with the soil wetness. Add more moisture in there, and we know from our oceans talk that water has a very high specific heat capacity. So if you add it to the soil, you increase the heat capacity of that soil. The moist soil has a lot more heat capacity than dry soil. The other part is the amount of energy available, and that just means the temperature gradient between how hot is the surface. If the surface is very hot and the underlying ground is very cold, there'll be more energy transfer. All right, the same graphs as before. The conductivity considers how fast energy can propagate, and the heat capacity considers how much energy it takes to change the temperature. You can combine these two terms. Specifically, you take thermal conductivity and divide by the heat capacity to get something called thermal diffusivity, large K sub S. Thermal diffusivity, using the combination of those factors, tells you how fast a temperature wave propagates into the ground. So what would this curve look like? Little ks, the conductivity, over the heat capacity. What does it look like? You can see here at the initial stages, the conductivity increases quite quickly. It's increasing faster than the heat capacity is increasing. As a result, the numerator is increasing faster than the denominator. Given the ratio here, that means that the diffusivity has to increase initially. So graphs A and B both have that increase initially, so they both could be correct here. However, after about the midpoint here, the conductivity slows down, so the numerator is not increasing as fast as the denominator. That would make this simple equation decrease. And so the answer here is B, where thermal diffusivity increases initially with some soil moisture, meaning you can get a temperature wave to go quicker into the ground. Say if you wanted to heat a basement by having a hot ground, that would be nice to have that amount of soil moisture. You can move heat down that quickly. But once you become really, really saturated in the soil, the diffusivity goes down. And this makes sense because the heat capacity becomes so large at that point, you need so much more energy to raise the temperature of that moist soil, the diffusivity just falls off at that point. What we're looking here is the upper graph looking at the diurnal cycle of temperature at different soil depths. So at 1 centimeter, 10 millimeters, right below the surface, here you see maximum warming, maximum solar radiation is probably at 12 noon here, and you get the maximum temperature not far off from that, at just 1 centimeter down, as you'd expect. If you want to go down 5 centimeters, though, it's going to take longer for that energy to reach that point. If you want to go down 20 centimeters, it's going to take almost till 8 p.m. for that energy to reach its maximum down there. And if you want to go down to 80 centimeters, or almost a meter here, you're not going to see, over the course of one single day of heating, any effect in that deeper soil. It just doesn't reach that far. There's not enough of a heat change at the surface to penetrate that deep into the soil over a course of a day. Now the annual wave, lower right here, penetrates to 14 times the depth of that diurnal wave. So over the course of a year shown here, there is enough of a long-term heat anomaly that it does push deeper and deeper and deeper in the soil, but there's a huge temperature lag here. So here we're looking at 10 centimeters down with this bold black curve here. So the maximum warmth time of year at the surface is probably around July, mid-July or so, and it's pretty well in tune with about 10 centimeters down. If you want to go down a meter though, you're not going to get that warm anomaly. The temperature wave takes some time to reach that. It takes a really long time to reach 5 meters down. It takes almost well into the fall before that heat at the surface made it down that far. And then finally, to get down to 10 meters, you're actually getting your maximum amount of heating at 10 meters in the heart of the cold season because it took that long for energy to go that far down. Looking at a few of these terms again, here's net radiation in the upper right. You can see that this clearly follows the path of the sun over the course of the year pretty well. There are some variations with long-wave radiation, but in general you have a big excess when the sun's most directly overhead at the solar declination, and then you have deficits towards the poles, especially the wintertime pole. Sensible heating on the upper left here, the reds and yellows are showing where the hot surface is warming the overlying atmosphere through sensible heat exchange, and the blue colors are showing where a hotter atmosphere is warming the surface through that same sensible heat exchange. And clearly you can see here some hot zones over the deserts. As we know, desert surfaces are very hot. The sands become very hot over time. If you have a hot ground and you have overlying atmosphere that's not as hot, you're going to get a big sensible heat exchange. And plus, In the deserts, you don't have an ability to get a latent heat exchange. There's no moisture to evaporate. So the energy is forced to go either into conductivity in the ground, and it turns out that deserts aren't that conductive, or it has to go into sensible heating of the atmosphere. And of course, in the polar regions where the surface is quite cold, you also can get a lot of negative sensible heating, meaning it's going from the atmosphere to the colder ground. Now looking at the latent heat flux in the lower left, red values here are showing active evaporation and turbulent transfer of that water vapor upwards, and you can see a lot of evaporation over the dried subtropical oceans. And it turns out that subtropical oceans are definitely the dominant source of the world's water vapor if you look in a global sense. You can also see some interesting things like high evaporation rates off the Gulf Stream as a function of the temperature of that water, especially during their wintertime season. You do see some negative values here where there's probably deposition, frost formation, or dew formation over time. And the last term here is the storage change. This simply means in blues here, the ocean's storing heat. It's going into the oceans, and the reds means it's coming back out. So typically you see oceanic heat coming out during the winter and going into the ocean during the summer. And so you can clearly see that the oceans in general dominate these storage changes, just showing that the oceans are a big heat storage mechanism. These three graphs are looking at the day-to-night variation of components of the surface energy budget for three different kinds of surfaces. The first one's in the Gobi Desert at 45 degrees north, a mix of sand and pebbles in August. You can see the net radiation coming in here. There's a deficit at night. You get an excess during the day, then it goes back down to a deficit during the nighttime. Most of that goes into sensible heating because there's no water to evaporate. Some of it goes into conduction into the ground because the surface is actually somewhat conductive. You can move some heat away from the surface into the ground. At nighttime, when you're running a deficit on radiation, you do get some of the heat coming from the atmosphere by sensible heating to the ground, and you get some of that heat back, a little bit of it back from the deeper soil too. With moisture here at 49 degrees north in May, we have a different budget here. We have a net radiation excess during the day. A lot of it, because there's moisture around, goes into latent energy exchange, evaporation of that moisture. Because there's more moisture in the soil, it's way more conductive too, meaning a lot of energy can go into the deeper ground, leaving less energy to sensibly heat the atmosphere. At night in the moist bare soil area at 49 north, you're running a deficit on radiation as the surface really is radiating long-wave radiation to the atmosphere effectively, but you are gaining heat to the surface from the deeper soil because you pushed heat into the deeper surface during the day with a high G value. Finally, the dry lake bed in the Mojave Desert at 35 north. You don't have any water to evaporate at the surface, so most of the net radiation excess goes into sensible heating of the atmosphere. However, you see the G terms not zero here. It's actually pretty high. And this is because in these dry lake beds, the water table is not far beneath the surface. So the soil can actually be pretty conductive a little bit deeper down and help remove heat from the surface into the deeper soil. So as you push that heat in during the day, it can come back out during the night to give you a source of warmth at night from the deeper soil when the atmospheric temperatures are colder. So why does this high lat location in the middle have the highest net radiation? It's certainly not because they're having the most solar intensity. That would be the Mojave Desert here at 35 north, very close to the summer solstice. So they have more top of the atmosphere radiation, but the net radiation at the surface is lower than it is for this area at 49 north at the 30th of May. The question is why? Well, it's definitely not a cloud effect. You can see that there's no clouds interfering with the net radiation. It's a nice bell curve, so it's not a cloud effect. One can imagine in late May at 49 degrees north, the ground's certainly going to be colder in general than these two deserts in the middle of summer. So if the ground is colder, that means lower IR will be emitted upwards. Since the IR flux upwards is a negative value for net radiation, if you lower that negative value, your net radiation goes up, and that's part of the reason. The other reason is that it's probably lower albedo here too. Deserts are fairly reflective. Finally, looking at the annual variation in the surface energy budget for a couple different locations here. Yuma, Arizona, quite a dry place, desert area. Most of the excess of radiation during the warm period goes into sensible heating in the atmosphere. Not a lot of latent exchange happening because there's not much water to evaporate. Not a lot of conductivity in the soil as well. Loosely packed sand grains don't conduct heat very well. San Antonio, very humid place. They have a lot of net radiation coming in over the course of the year. A lot of it goes into latent energy. So you're evaporating water from the surface, raising water vapor amounts, raising the humidity of the atmosphere there. Some of it does go into sensible heating, enough that you have kind of a deadly mix of heat and humidity there that makes it kind of uncomfortable to be outside at times. And since the ground is pretty moist, it's fairly conductive, you can move some heat into the ground during the heart of the warm season, and some of it will come back up. Copenhagen, Denmark, being a very high latitude, the net radiation is lower here. You can also see there's a long deficit of net radiation during their long cold winter. And during that time, they're still evaporating water. There must be winds happening to do that. But they also have sensible heating coming from the atmosphere, which is warmer than the surface. So the surface is effectively just cooling off really, really well by radiation. So the atmosphere actually is giving heat to the surface during the winter because it's warmer than that surface during that time. They also get a little bit of heat back that was stored in the surface or in the deeper soil during their warm season, comes back and gives the surface a little bit of heat during their cold season.